So we're going to have one function, f of x, which is x cubed plus 1. And we're going to have another function, u, which is equal to x squared. And we are going to try to find each of these three antiderivatives, or these three integrals. And we're going to put all of our final answers in terms of x. But you should hopefully note that all three of these integrals, while they are similar and related to each other, are all a little bit different, right? We have the integral of f of x dx. So that's going to be the easiest one. We're just going to integrate x cubed plus 1 in terms of x. And then we're also going to integrate f of u du. And we're also going to integrate f of u dx and see how these are different from each other and see how the variables matching up matters. So first off, f of x dx. Well, what's f of x? F of x is just x cubed plus 1, right? So I just need to integrate x cubed plus 1 dx. And what's the integral of x cubed plus 1 dx?
X to the 4th over 4 plus x.
X to the 4th over 4 plus x. And you forgot something important, plus your constant. Don't forget the plus a constant place. Everybody good with that part? That part should be pretty easy. All right. So we've now got the integral of f of u du. So what's f of u, first off? And we needed what to be our variable within here. The variables need to be u so that we can integrate with terms of u. So what's f of u? You don't need to think about this yet. What's f of u?
U cubed plus 1.
Right, it's just u cubed plus 1. I have no idea what just happened there. What the world just happened? All right, that's better. All right, u cubed plus 1. Right, that's what f of u is. So what's the integral of u cubed plus 1? It ought to just be u to the 4th over 4 plus u, plus our constant. But we were asked originally to put this all in terms of x. And so now we will use this u equals x squared to put this in terms of x. What does that give us? X to the 8th over 4 plus x squared plus our constant. Everybody good with that?
Yes.
Okay. Now, what about this one, f of u dx? Well, that ought to be the integral of u cubed plus 1. That's f of u, right? Dx. So we need it in terms of x, which means we need to, in order to integrate it, we have to have it in terms of x, which means we need to convert u cubed plus 1 into x before we integrate. So if u is equal to x squared, what is u cubed plus 1?
X to the 6 plus 1?
That would just be x to the 6 plus 1. And if we integrate that, that ought to give us x to the 7th over 7 plus x plus a constant. So hopefully we note that these variables over here matter, right? That if we did f of x dx, we get one thing. If we do f of u du, we get something else. And f of u dx is a completely different thing. And the biggest thing that we probably want to note is that these two, f of u du and f of u dx, are very different from each other. We're going to use this idea where we have a function within a function, or a substitution here that we're going to make where u is equal to something in terms of x to help us to integrate some functions that we might not normally be able to integrate. So let's take a look at this one, sine x times e to the cosine x. So if you think about the list of integrals that I gave you, is an integral that looks just like this one on the list anywhere? Is this just a simple rule that we can follow and integrate and get an answer?
No.
No, exactly. So we're going to have to substitute some portion of this out. And this is not a rule that you follow 100% of the time, but it's a general rule. Look for the piece of it that's most complicated and substitute out either all or part of that piece. So if I have sine x e to the cosine x, which piece of that is more complicated?
E to the cosine x?
Exactly. And e to the cosine x is more complicated than sine x. You know what sine x looks like, right? You might not know what e to the cosine x's graph looks like. So we're going to either substitute out all e to the cosine x or just part of it. And in this case, only part of e to the cosine x is what's causing the problem. If I just had e to the u, could I integrate e to the u?
Yep.
Yeah, I should be able to integrate that. So let's just substitute out the cosine x part, which would give us an integral of sine x times e to the u dx. And what's the problem with this integral at this point?
It's e to the u, but it's asking for dx.
Right, it's got a u in it. It's also got x's in it, and it's got a dx. Now, we were talking about it being pretty straightforward to just integrate e to the u. So it'd be really cool if I could have e to the u du in here. So is there a way for me to figure out what du is equal to? Well, yeah, du is just the derivative of u. So it should equal the derivative of cosine, which is negative sine x dx. So let's see if we can replace stuff in here with a du. Do I have a negative sine x dx over here that I could replace with a du? I have a dx, right? And I have a sine x, but I don't have the negative sign, do I?
No.
No. Well, can I just put a negative sign in there?
That seems not legal.
It is not, right? I can't do that unless I do something that cancels that out. So how can I cancel out a negative sign? By
Put a
putting
negative on the outside too.
Yeah, I just put another negative, right? The negative sine x e to the u dx is the same as sine x e to the u dx, right? If I put two negatives, that doesn't affect anything. And now I have perfectly matching up a negative sine x dx and a negative sine x dx on the inside. And so I should be able to rewrite this as an integral, sorry, an opposite of the integral of e to the u, because that's still there. And then negative sine x dx, I'm going to replace with du. Everybody see that? Are you good with that? Okay. Note that this negative sign could stay outside when I integrate, or I could bring it inside and integrate, and either way is perfectly acceptable. But what's the integral of e to the u?
E to the
E
u.
to the u.
Just use the u. So I have a negative e to the u and a plus a constant. Now, technically that negative was outside of this whole integral, e to the u plus a constant, right? And if I were to distribute this minus sign through, I'd have minus e to the u minus a constant. But generally, when we're just doing these indefinite integrals, this plus a constant, whether it's plus a c or minus a c or plus a half a c or whatever it might be, those are all still just constants. So we normally just write it as plus a c. So this would be negative e to the u plus c. And all we have left to do is replace the u's back with x's and get negative e to the cosine x plus our constant. And that's our answer. Everybody good with that? Any questions on that? On that process? That's what we're going to be working on for pretty much the rest of the day today, with ones that get more and more complicated as we go. So let's make sure we understand the basics of it. Any questions? Or are you guys good?
So if you evaluated the integral and you like took the derivative, it gives you the same function as before.
I'm sorry, say that again.
So if you took the derivative of the integral, it gives you the same function as before. So we can check it like that, right?
You most definitely can. And I'm not going to bother to take the derivative with the plus c in there because we know that goes away, right? But the derivative of negative e to the cosine x, well, that's a chain rule problem, isn't it? That's the derivative of negative e to the u with u equal to cosine x. So that becomes negative e to the cosine x times the derivative of cosine, which is negative sine x. And the negatives cancel, and we've got e to the cosine x times sine x, which is exactly what we started with. But yes, you can definitely check it that way. Good?
Yeah.
All right.
Wait. Could you go back and explain how you got du equals negative sine x dx again?
Yep, I just took the derivative of u using a differential. That's just du, and the derivative of cosine x is negative sine x dx. Any other questions on that? I want to make sure everybody's good with that first one because, you know, the first 2 or 3 here we're going to do are going to be pretty straightforward, but then they're going to get more complicated. And then tomorrow we're going to finish up with some that are even more complicated than what we do today. So, any other questions on that first one? All right, let's take a look at this. We have an integral of x squared times the square root of 5 plus 2x cubed. So, first question you want to ask yourself as you're working through this is, what piece of this is most complicated? Is x squared more complicated, or is the square root of 5 plus 2x cubed more complicated?
The square root.
Right, the square root of 5 plus 2x cubed. So we either want to substitute out all of that or substitute out a piece of that. So do you guys want to substitute out the entire square root of 5 plus 2x cubed, or do you just want to substitute out the 5 plus 2x cubed? Just the 5 plus 2x cubed? Okay. And if I do that, what would du equal? It should be the derivative of this, which is just 6x squared dx. And hopefully we will recognize that we almost have a 6x squared dx in here. All we have to do is add in the 6 on the inside, which means we need to put a 1/6 on the outside to cancel out the 6. Good or no?
Good.
Cool. So now we have the 6x squared and we have the dx. They can be replaced as a du. So we've got 1/6 the integral of root u, or u to the 1/2 du. And what does that integral become? It's 1/6, and the integral of u to the 1/2 is 2/3 u to the 3/2 plus our constant. And like I was saying before, 1/6 of a constant is still just a constant, so I don't need to write 1/6 c. I'm just going to write c. And I'm going to distribute the 1/6 then to the 2/3 u to the 3/2 also, which gives us 2/18 or 1/9 u. And what was u? U was our 5 plus 2x cubed to the 3/2 power plus some constant. Any questions or issues with that one?
Why did we put a 1/6 at the beginning for like red?
Yeah, so the reason we did that was because we knew that we needed to replace some stuff within here to turn something into the du so that we could integrate this root u du. And so what we needed was a 6x squared dx, and all we had was an x squared, so we put a 6 on the inside, and then we put the 1/6 on the outside, so that effectively if I multiply by 6 and I multiply by 1/6, it doesn't do anything to the integral other than allow me to substitute out this 6x squared dx for a du. But the 1/6 has to stay because it doesn't get substituted out with anything else.
Okay, got it. Thanks.
Yep. Any other questions on that one? All right. Let's do another one. This one's going to get just a bit more complicated. So, what's the first thing you think we should do with cotangent 7x?
Possibly make 7x a u.
All right, so one thought is u equals one thought is to make u equal 7x, which would let du equal 7 dx, right? So if I were to do that, that's going to give me eventually, once I do some other work, I'm going to get a cotangent u inside of here. And is there a formula or a rule that we have for integrating cotangent u? On our formula sheet?
No.
No, there's not. So we're going to have to do a little something else here to figure this one out. So it's a good idea. If we knew the formula for cotangent's antiderivative, which in just a minute we're going to figure out what that is, then we could make that substitution. But now, for right now, we're going to have to rewrite this as a different integral using different trig functions. So the only real good way to rewrite cotangent 7x probably is cosine 7x over sine 7x. And if we were to do that, generally when we have a fraction, we're going to want to substitute out the denominator of it. So we're going to substitute out u equals sine 7x. And if u is sine 7x, what is du going to be?
Seven cosine of 7x dx.
7 cosine 7x dx. Good. I'm glad you remembered the chain rule on that. So do I have 7 cosine 7x dx? Not quite.
Oh.
I have close to it. I have cosine 7x, so I'll put in a 7. And if I put in a 7, I have to cancel that out by multiplying by a 1/7 also. Good or no?
Good.
All right, so now we've got 1/7 of the integral. And in the numerator, I have 7 cosine 7x dx, which is exactly my du. And in the denominator, I have exactly my u. And on your sheet, you should have an integral of du over u. What's the integral of du over u? All right, you guys got to get these memorized. The integral of du over u is natural log absolute value of u plus a constant. And so that gives us 1/7 the natural log of the absolute value of sine 7x plus a constant. All right, this is u to the -1, right? You can't integrate that by going up to u to the 0 and dividing by 0. But we do know that the derivative of natural log is natural log of x is 1 over x. So the integral of 1 over x ought to be natural log of x. And the reason we throw it inside of absolute values is because 1 over x is defined for all real numbers except 0. But natural log of x is only defined for positive numbers. So if we put it in absolute value, it becomes defined for all positive and negative numbers. So it has the same domain then as our 1 over x function does. But everybody good with that or no?
Question like pertaining to the homework too. So du over u is the same thing as 1 over u times du, right?
That's correct. That is 100% correct. All right, real quick, I'd like to go through now, and there's a couple of other integrals which you can solve using u-substitution, but oftentimes it's helpful just to have them memorized. So the integral of cotangent x dx and the integral of tangent x dx. So we sort of just did this cotangent x dx one, except we had a 7x in it. So cosine 7x, we just did 7x, and so I wrote a 7x. Cosine of x over sine of x dx with the u substitution that u is equal to sine x and du is cosine x. So this becomes du over u, which is natural log absolute value u plus your constant. So the integral of cotangent x is equal to natural log absolute value of sine x plus a constant. So if you choose to memorize that, it might be helpful to you. But you can always just go through and do this simple u sub if you forget. Now, in teaching these classes, I use them often enough that I just memorize them. And in BC, so if you're planning on taking BC or Calc 2 in college, you might as well just memorize it because it pops up so often that it's just helpful to know. And we could do the similar thing here with this one. We'd rewrite this as the integral of sine x over cosine x. Still substituting out the denominator, but this time it gives us a negative sine x dx, so we'd have to put in a negative and a negative, giving us the opposite of the integral of du over u, which is the opposite of the natural log of the absolute value of u plus a constant. And so we would say that the integral of tangent x dx, dx over there, is equal to negative natural log absolute value cosine x plus a c, which is sometimes written as this natural log absolute value secant x plus a constant. So if you want to memorize those, that might be helpful. They're not on your sheet, but they do show up often enough that it might be nice to not have to write out the u sub every time. Good or no? All right. Let's move forward. Let's look at dx over cosine squared 2x. So take a second and think about how you might want to go about starting that problem. Anybody have any ideas on how to start this one?
I would probably want to turn the 1 over cosine squared of 2x first into just secant squared of 2x.
That sounds like a great idea. So oftentimes we want to rearrange our trig functions so that we have something relatively familiar up here. The integral of secant squared is one of our simple formulas, right? So the only problem is the 2x that's in here. We need to get rid of the 2x. So we'll do that using u-substitution. U equal to 2x and du equal to 2dx. So all we need to do is add in our 2 and our 1/2 to cancel each other out. And we have 1/2 of an integral of 2dx is our du. And now we have secant squared u du. And the integral of secant squared u is just tangent u plus our constant. You got to have those ones on that sheet memorized. This gives us 1/2 tangent 2x plus a constant. Any questions on that or no?
Could you have done it without turning into secant squared, like substitute the cosine?
Nope, you could not have. Would not have worked out. Any other questions on that one, or everybody good there? All right, let's take a look at this one. Cotangent squared 3x dx. So what are we going to do with that one? Any thoughts on that?
Well, I don't know how useful this would be, but there's a formula that's like tangent squared of x equals secant squared of x minus 1.
True. There's also one for cotangent squared. Cotangent squared of x is equal to cosecant squared of that value minus 1. And that's exceptionally helpful, right? You should know, you got your original one, right? Sine squared x plus cosine squared x equals 1. Well, there's also 1 plus tangent squared x equals secant squared x. And you should also know that 1 plus cotangent squared x equals cosecant squared x. So cotangent squared is cosecant squared minus 1. And so this is actually exceptionally helpful because part of this, the integral of cosecant squared 3x, can be separated off by itself. And then on the other part of it, I just have a minus 1 dx, which can be integrated on its own. And cosecant squared has an integral that we should easily be able to find. And what would that be?
Negative cotangent?
Negative cotangent. But before we can do that, we're going to have to substitute out that 3x. So I'm going to have to put in a 3 and a 1/3. So we're going to end up with 1/3 the integral of cosecant squared u du. And then over here, we're going to have minus what's the integral of 1 dx. Should just be
X.
just x plus our constant. And then the integral of cosecant squared u ought to be negative cotangent u plus some other constant. So I'm going to have plus a constant and plus another constant. which is just going to be plus a constant. And then we'll replace the u with negative 1/3 cotangent 3x minus x plus c. Any questions or issues on that? All right, let's do another one. Cosine cubed x. So I want you guys to take a second and think about how you might go about starting this one, because this one gets a little bit, not super complicated, but a little more complicated. How are we going to go about this one? Any thoughts?
Would splitting it into cosine squared and a cosine help?
Cosine squared and a cosine. Yeah, that's going to be our first step. All right, so we're going to split that into cosine squared and cosine. And what am I going to do from there?
Can you make cosine squared x equal 1 minus sine squared x?
Hold on one second, everybody. This is all good so far. Give me 1 second. Okay, sorry. I was checking my kid's math homework and he missed a couple of problems, the greatest sin of all time. And then he forgot which ones he missed. So he was yelling from the other room to fix them. All right, what are we going to do from there? 1 minus sine squared x times cosine x. Anybody?
Do a u-substitution for cosine x.
All right, so let's take a look at this. A u-substitution for cosine x is going to give us du is equal to negative sine x dx. Do you have a negative sine x dx in there to cancel out? Or any way to get just a simple negative sine x in there? Unfortunately, I think the answer to that is no, there isn't. So no, this is not going to work out. Any other ideas on the substitution there? I wasn't writing anything. I was just waiting on somebody to say something, Julian.
Would you just split up the integral into like the integral of cosine x plus the integral of negative sine squared x times cosine x?
Okay, so we could do that. So let's do that. The integral of cosine x minus the integral of cosine x sine squared x. Now, the first one, the integral of cosine, is easy, right? That's just sine x. So we still got to deal with this one. How am I going to deal with that one? Anybody got a substitution there?
Could you substitute sine x squared?
Let's take a look at that. So if we try to do u is equal to sine squared x, then du is 2 sine x cosine x dx. And that's a little bit of a problem. I've got the cosine x dx, and I could put in the 2, but putting in a sine x is a little bit more of an issue because that's not a constant. I don't think that's going to work. You guys are thinking too complicated. Go simpler. Okay, I see a cosine x there. No, I won't just substitute u equals cosine x now because then du is negative sine x dx. A negative is easy enough, but I have 2 of those. I have sine squared, so that's going to be a problem. I could write sine squared as sine times sine, but I don't need to rewrite anything. This is already perfectly set up for a really, really simple u substitution that for some reason second period had a really hard time finding also. And every class every year does. And it's fun for me to watch you guys struggle, even though I'm not getting the opportunity to actually watch you struggle this year. I know in my mind that you're struggling and it's fun. What can you be? No rewriting, no adjusting using trig functions, no nothing else, just do a substitution. All right, Alicia, you got it. We're just gonna substitute u is equal to sine x, because what's du? Cosine x dx if we do that. There's my cosine x dx, and my sine squared just becomes u squared du. And u squared is easy enough to integrate, right? That's just u cubed over 3 plus our constant, or sine x minus sine cubed x over 3 plus a constant. Anybody have any issues with that? All right. I want to go back to right here before we separated it into two different functions. Okay. So real quick, I'm going to do this on a new page. We could have had, or we had this, we had 1 minus sine squared x times cosine x dx. And right here at this point, we could have also, instead of separating it, made the substitution that u is equal to sine x with du equal to cosine x dx. Because that would just give us an integral of 1 minus u squared du. So we actually did more work than we needed to do, because this just gives us u minus u cubed over 3 plus a constant, which when we plug it in is sine x minus sine cubed x over 3 plus a constant. Everybody see that we could have done that substitution even earlier than we did? Hopefully. Everybody feel okay about all of this or no?
It mostly makes sense.
Mostly makes sense. All right. Mostly is mostly okay. Let's do some more. Let's see if we can come up with some good solutions for some of these. Yeah, more practice for sure. Don't worry, we're going to have plenty of practice on this, and you're going to have plenty of practice on these with your homework tonight. All right. This one's a little different also because we've got a definite integral here. So we're going to spend a little bit of time working with this one, doing it in a couple of different ways and seeing some interesting stuff about integrals here. So the integral from 0 to pi over 3 of tangent x secant squared x. So we've been doing all u subs, and I'm going to tell you right off the bat, this one has a nice simple u sub that we can use to start with. So what substitution do you want to make?
Tangent x.
Great idea. If u is tangent x, then what's du?
Secant squared x dx.
Squared x dx, and we've got that sitting right there already. This just becomes an integral of tangent x, or u, secant squared x dx, or du. Now, we have a small issue though. Because this is a definite integral, we've converted variables. What are these 0 and pi over 3? They are x values, aren't they? But I can't plug in x values to an integral with u's. So we have to go in and say, well, if u is equal to tangent of x, then if x equals 0, tangent of 0 is 0, which tells us that u is equal to 0. So this lower limit can stay as a 0, but since u is tangent x and x is pi over 3, the tangent of pi over 3 is what? This is where you should all unmute yourselves and immediately tell me what the tangent of pi over 3 is. It is this is the part of class where I normally start like hitting the whiteboard and yelling because I'm so angry that nobody knows the tangent of pi over 3 off the top of their heads.
Root 3.
Yes, thank you. Root 3. So we have to convert these into u values up here. They can no longer be x values because we converted everything into terms of u. So our limits of integration have to change as well. Everybody okay with that? Now, the good news about this is, for one, this integral of u is exceptionally easy, u squared over 2. And the other good news is, since this is a definite integral and we've switched our limits of integration to 0 and root 3, we don't have to convert this u back to tangent x and convert these 0 and root 3s back to 0 and pi over 3. We can just evaluate it as is. So root 3 squared over 2 minus 0 squared over 2, which is 3/2. Good or no?
Right, how did you get u squared over 2 in the...
I just integrated u. Right? That's
okay.
u to the first power, so it goes after u to the second and divide by 2. Any issues there or no? All right, I want to go through and try this problem with a different substitution. So we had the integral from 0 to pi over 3. And what do we have? We had tangent x secant squared x, right? Couldn't I have written this perhaps like this? Would you guys all agree that those two are the same thing? Oh, good. Somebody said yes in the chat. Perfect. So I could have done a substitution where u was secant x and du was secant x tangent x dx. You guys agree with that? We've done the same thing there. And this would give me an integral of secant x is u and secant x tangent x dx is du. But we have to convert these limits again. And if u was 0, what's the secant of 0? Or sorry, if x was 0, what's the secant of 0?
1.
1. And what's the secant of pi over 3?
2.
2, right? The cosine of pi over 3 is a half, so 1 over a half is 2. So this looks like the same integral, except different limits. Well, u squared over 2 from 1 to 2 is 4 squared, 2 squared, which is 4, over 2 minus a half, which is 3 halves. So either substitution would have given us the exact same numeric value, which is good because they both look like they should work, so they should give us the same answer. Everybody good there?
Yes.
All right. Now, I know you're all sick of this tangent x secant squared x problem, but we're not done with it. I'm sorry. Let's forget about the limits of integration for a second and pretend that we had done this problem as an indefinite integral. So if we just had the integral of tangent x secant squared x, one way we could have done it was with the substitution u was tangent and du was secant squared. And the other way we could have done it, I'll try and do this in a different color so that it look weird, was that u was secant and du was secant x tangent x. Everybody agree? We just did it both ways, right? With u was tangent and with u was secant, and it worked out. So with this method, we ended up with the integral, let's see if I can do that in a different color. We ended up with the integral of u du, which gave us u squared over 2 plus a constant, or tangent squared x over 2 plus a constant. On this side, when we got the integral of u du, it still gave us u squared over 2 plus a constant, but it gave us secant squared x over 2 plus a constant. And clearly these do not look the same. True?
Yeah.
But they both gave us the same numeric result, right? But we know that tangent squared of x is not the same thing as secant squared of x, because this is sine squared x over cosine squared x, and this is just 1 over cosine squared x. They're clearly not the same thing. Well, that's okay. And it may not seem like it's okay, but it's okay if the integral you get doesn't look exactly the same as perhaps the integral that I get as my answer, or the integral of the person that you're working with, right? these two things are actually sort of the same. They differ in the value of this constant. And we're going to just take a second to look at why that's the case. So we have tangent squared x over 2, and I'm going to say plus constant 1. And over here, I'm going to say I have secant squared x over 2 plus constant 2. Right? Because a constant is a constant. Any constant is a constant, whether we label it as C1, C2, C3, C1000, just C. It just means a constant. And those constants don't have to be the same thing. And in this case, they're not the same thing. We talked a minute ago about secant squared x being equal to what? 1 plus tangent squared x. So on the left-hand side, I'm just going to leave things how it was. But on the right-hand side, I'm going to convert that into 1 plus tangent squared x over 2. And so on the left, I still got tangent squared x over 2 equals constant. Over here, I now have 1/2 plus tangent squared x over 2 plus constant 2. And so we can see that this and this are the same. And it tells us that the constant, if we use tangent squared x over 2, has to be equal to a constant if we use secant squared x over 2 plus 1/2. So we can see that they only differ by a constant. And so constant 1 being constant 2 plus 1/2 doesn't really matter, right? That constant, if you were to take the derivative to try to get back to the original function, whether it was a constant or a constant plus a different constant, would still cancel out when you took the derivative. Does that make sense? Why it's okay for us to have two slightly different looking answers that are both correct. That's a lot of silence there. Okay. When you take an integral, it's okay if the integral you get differs by a constant from the integral that I might have gotten. That's the whole point of all this. And as you get into higher calc classes and beyond, and courses like differential equations, these constants begin quite a bit. And you need to be able to understand the relationship between the different constants and recognize that, you know, many different integrals have many different looking answers that either are equivalent to each other or differ by a constant. And it's okay if they differ by a constant. Anyway, that's my point about all of that. Any questions on any of that or no? All right, let's move forward. Let's do a couple more of these and then we'll be done. We have the integral from 0 to 1 of x over x squared minus 4. So anybody see a good u-sub here?
Make the denominator equal to u.
All right, so let u equal x squared minus 4 and du equal 2x dx. So do I have a 2x dx? Nope. So we'll put in the 2, which means we'll put in the 1/2. And so we're going to get 1/2 of an integral of 2x dx is just du, and x squared minus 4 is u. The only thing we still have left to do is to figure out what our new limits of integration are because we've converted from x to u. So 0 squared minus 4 is -4, and 0 squared minus, sorry, not 0 squared, 1 squared minus 4 is -3. So we're going to integrate from -4 to -3 now. Everybody good with changing this integral into this new one?
Yep.
All right. So we still got a 1/2. The integral of du over u is natural log absolute value u. And it's now evaluated from -4 to -3, which gives us 1/2 the natural log of the absolute value of -4, which is 4, minus 1/2 the natural log of the absolute value of -3, which is 3. And this answer right here is a perfectly acceptable answer. Oh, why did I write those backwards? I don't know why I wrote those backwards. Sorry. Three and 4, upper limit minus lower limit. I'm not sure why I did that. So this is a perfectly acceptable answer, especially if it was my quiz or a free response question on the AP test. But be able to convert your logarithms around, because you might end up with something like 1/2 natural log of 3/4 as a multiple choice answer on the AP test, right? Using log minus log becomes a division in one logarithm. Or you might even see that this becomes a power within here. So you could have natural log of the square root of 3/4 or natural log of √3/2. Any of those would be fair game as an answer on a multiple choice AP question. So make sure you can do those conversions. Any questions or issues with that one? All right, let's do one more. This will be the last one we do today. Can anybody see a good u-sub?
X² + 9.
Sounds like a good one to me. Let's let u equal x² + 9 with a du equal to 2x dx. So do I have a 2x dx?
Almost.
Yeah, I mean, I've basically got it there, right? I've got a 2 times a 2x. So what can I do with the extra 2? I can just take it and throw it outside that integral. 2 times the integral of 2x dx over root u. And now the 2x dx can become a du. And we've got 2 times the integral of u to the -1/2 du. And what's the integral of u to the -1/2? That goes up to become u to the +1/2. And you divide by 1/2, which will give you a multiplication by 2. So 4u to the 1/2 plus our constant, or 4 root x² + 9 plus our constant. Good there or no? All right. Now, I promised that was going to be our last one, but I sort of lied. I want to go back and remember that cosine cubed one we were dealing with? Where was it? Somewhere in here. There it is. Remember when we got to this point, 1 minus sine squared x times cosine x? And we split it up into 2. And we said, well, we could have done that without splitting it up into 2. Well, this second method that we did here was the easier way. But I want to take a look at something else we could have done with this that actually would have made it a little bit more complicated. But it's going to be a good intro to what we're going to be doing tomorrow. So it shouldn't take us too long. We've got 1 minus sine squared x times cosine x dx. So one thing we could have done, and somebody in second period suggested this, and then I came back to it later because I was like, I don't want to deal with that right now, is we could have factored the 1 minus sine squared x into 1 minus sine x times 1 plus sine x times cosine x. That looks horrible. So we're going to rewrite the cosine x. And we could have made a different substitution. We could have gone in and said that u was equal to 1 plus sine x, and that would make du still equal to what? For those of you that are still alive out there listening, cosine x dx. So I could have subbed out all of this junk, except for the 1 minus sine x, into a u and a du. But we still have a problem, which is 1 minus sine x, right? Everybody agree that that's a problem?
Yes, it's a problem.
Yeah, all right, good. Somebody's still alive. So what we can do is we can take this u equals 1 plus sine x and say, what is sine x equal to? Sine x is equal to u minus 1. And so we can go in and rewrite this integral now as 1 minus sine x, which is u minus 1, all times u du. And we should then be able to simplify that down to an integral. We have 1 minus u, and we have minus a negative 1, so that becomes a 2 minus u times u du, or an integral of 2u minus u squared du. Everybody see that we could have done that?
Yep.
Cool. So, and now obviously this is more complicated than what we did do, but it's going to illustrate my point about constants and sort of introduce what we're going to do tomorrow. So the integral of 2u minus u squared is just u squared minus u cubed over 3 plus a constant, which ends up being what? Sine squared x minus sine cubed x over 3 plus a constant. And if we note, this is very different looking than what we had before, right? This sine squared x, was it minus or plus? Minus sine cubed x over 3 plus some constant. And on the, when we had done it previously, what did we end up with as our answer? We'd ended up with just sine x minus sine cubed x over 3 plus some constant. True? You guys agree with that?
Yeah.
Okay. Yeah. All right. So what we're going to do is, that is what we ended up with, right? Sine squared x minus sine cubed x over 3. So if we wanted to, we could go through here and we could simplify out some of these terms in here and see what happens with our constants. And I think we're sort of out of time, so maybe we shouldn't bother doing this right now. Yeah, maybe we should just stop where we're at here. But if I were to go through and simplify these, we'd find out that these just differed by a constant. And we'll say that's good enough for now. I won't bother going through there. But they do differ by a constant. If you want to see how that works, you can go watch second period's lecture video. Apparently Claire is starving, so we need to stop for her. Everybody good? See that there's lots of different ways to do these kinds of problems and all that fun stuff. Hopefully.
Wait, about that last one. So the the one we did at the end. When you like substitute 1 plus sine x in, all that just multiplies back into sine squared x minus sine cubed x over 3.
Sorry, say that again. If we substitute the 1 plus sine x, that makes this a u and a du with a 1 minus sine x left over.
Right, but when you sub it back at the bottom, it just makes sine squared x minus sine cubed x over 3.
Oh, I'm sorry. Yeah, I put in the wrong thing, didn't I? Wow. Okay. Yeah, we got to go back and fix that.
Yeah, I was really confused about that.
Yeah, sorry. No, thank you. I was trying to hurry through and messed up that because this is a 1 plus sine x, right? Sorry, it should end up looking like that. Our substitution was 1 plus sine x, not just sine x. That's totally my fault. So we should have ended up with 1 plus sine x squared minus 1 plus sine x cubed over 3 plus the constant. And those ones should differ by the constant. That was my fault. I apologize. I got in that mindset of u is sine x since we've used sine x like 500 ways to do this one. All right, let's go through and do it. Now I feel bad like I should do this. So sorry, Claire, you're gonna have to starve for a minute. We end up with 1 plus 2 sine x plus sine squared x on this side. And then what's 1 plus sine x cubed? That's minus 1 plus 3 sine x plus 3 sine squared x plus sine cubed x. Do that distributing. We should do that. And now, like terms, we've got 1 minus a third, right? The 1 over 3, and 1 minus 1/3 is 2/3. We got a 2 sine x minus a 3 sine x over 3. So that's 2 sine x minus sine x. We got a sine squared x minus a 3 sine squared x over 3. So sine squared minus sine squared cancels. And then we just have the minus sine cubed x over 3 plus that constant. And so we should note, it's a plus sine x there. 2 sine x minus sine x is positive sine x. We should note then that what's the difference between these? Constant 1 plus 2/3 has to equal constant 2. So they only differ by the constant. They still have the same sine x minus sine cubed x over, that should be a 3. I don't know why I wrote an x there. Oh, that was unfortunate. They both have that sine x minus sine cubed x over 3 term. And then the constants are just off by a bit.